So here we're going to look at using trig identities to integrate. So often you will find, or you'll be asked to integrate something which you cannot integrate because you don't know the integral of tan squared. It's not a standard result that's given to us in the formula book, nor is it one that you know. So here in this particular question, as you can see here, integral of tan squared. Now, if we look at our formula book extract on the right hand side, we're trying to look for the integral of tan squared. Well, I'm trying to look for tan squared. Is tan squared appearing anywhere? I can't really see tan squared anywhere whatsoever. So then obviously it's going to be difficult for me to integrate that using a standard result. So as such, I'm going to use identities to get it into a form or a trig function that I can then integrate. So here I'm going to go and think about what identities we know that relates tan squared to maybe another trig function. So we know that one of the identities is sec squared, so I'll write that down here. Sec squared x is equal to 1 plus tan squared x, or sec squared x is identical to 1 plus tan squared x. So let's go and use that identity, and we're going to substitute instead of tan squared, we're going to substitute, rearranging that, it becomes sec squared x minus 1. So integral of tan squared x dx then becomes integral of sec squared x minus 1. Now, can we integrate sec squared? The answer is yes, because if we look at this here, we've got sec squared appearing here on the right hand side, and if we integrate that, should get you tan. Or alternatively, we can just look here, integral of sec squared kx is 1 over k tan kx. So let's go and integrate this then. So we're going to say here integral of sec squared becomes tan x. K is 1 in this case, okay, so it becomes 1 over 1 tan 1x, which is the same thing. And then integral of minus 1 becomes minus x, and so that plus c. Okay. So using identities to get it into a form that we can then integrate. You need to have your formula book beside you and look at to spot if there is an integral that you can get, or a function that you can integrate. Look at another example here. So it's a show that question in this case. So that means we need to integrate sine squared. Now, we don't know how to integrate sine squared x. Again, you can see here that it's not in our formula book, and nor is it one that we do know. But what we do know is we know some double angle identities that relate sine squared x to trig functions that we can integrate. So let's go and write that down. Cos 2x is equal to, or identical to, 1 minus 2 sine squared x is a double angle identity that we do know. If we rearrange that, we can get 1 minus cos of 2x is identical to 2 sine squared x, and therefore sine squared x is identical to a half minus a half cos 2x. So I've just written it in that form, dividing everything by 2. So I can then go to my integral here. We're integrating from the limits of pi over 8 to pi over 12, and we're integrating sine squared x dx. So instead of sine squared x, I can go and write down here, I'm integrating half minus a half cos 2x with respect to dx. Now I know how to integrate cos 2x. It's a standard result that we already know. So let's go and integrate this. Integrating half gets us a half x. And here, cos of 2x, remember when we differentiate sine, we get cos. So when we integrate cos, we get sine. Okay, so we'll end up with sine of 2x, and then we divide by 2. So we already got minus a half. That divided by 2 gets us a quarter. And then pi over 8 and pi over 12 as our limits. So we then go and substitute those, and substituting these in here should then tidy up and simplify to that. So here we're looking to integrate sine 3x cos 3x dx. So first of all, again, we don't know how to integrate this as it is. This is a product of two trig functions, so it's not the same as integrating sine 3x and integrating cos 3x. You can't do it like that. If they were separate terms, then we could have done this, but this is one whole term. So we will look in our formula book extract. Do we know sine 3x cos 3x? Does that appear anywhere here? I can't see it appearing anywhere in our standard results. So we need to think of a way of getting this into a form that can be integrated. So we know a double angle identity that actually is in this form. So remember, sine 2x is identical to 2 cos x, 2 sine x cos x, sorry, it's the same thing anyway. And this can be extended to, if I want to get sine 3x cos 3x from here, I need to then change my angles from x to 3x. So then if I change my angles, it then becomes 2 sine 3x cos 3x will then be identical to, what did I do? I doubled all my angles, so times them by 3, so I need to times this by 3. This would become 6x. So then this identity is also true. So we're going to use that identity. Now I need to get to that sine 3x cos 3x that I have in my question. So that's the same as saying sine of 6x over 2, or times by half, is identical to sine of 3x cos of 3x. So this is all using identities. Now I've used my identity to find out what sine 3x cos 3x is equivalent to. So then I can go and write down my integral again. And sine 3x cos 3x now becomes integral of a half sine 6x. So essentially we're integrating this with respect to x. So we know how to integrate sine 6x. When we differentiate cos, we get minus sine. So when we integrate sine, we get minus cos. So the integral of this then becomes, first of all, cos of 6x, the angle remains the same, but then we divide by 6. So a half divided by 6 gets us a 12th. And then we said we get minus here because when we differentiate cos, we get minus sine. Therefore, when we integrate sine, we get minus cos plus c. Okay. And lastly, one more here. You can take a look at part B. So we're integrating sec x plus tan x all squared. Now, if you look at this, first of all, there's a bracket and all of that is squared. So it doesn't look quite neat at the moment. I mean, we haven't learned how to integrate these types of functions yet, and I can't think of any identities. So the first thing which I'm going to do is I'm going to actually expand the bracket. So sec x plus tan x all squared is this, and so then this gets us sec squared x plus 2 lots of sec x tan x plus tan squared x. So this is what we're trying to integrate. So first of all, do we know the integral of sec squared? Well, this one we know how to integrate. Okay, we can integrate this because that's the standard result. Do we know how to integrate tan squared x? No, we don't, but we can write tan squared x plus 1 is identical to sec squared x to then get it into the form of sec squared x, which we do know integrate, so we'll be able to integrate that. And then we need to see, do we know sec x tan x? Is this a standard result, first of all? So if we look here, there's nothing on the box under integration, but on the differentiation box, we've got sec x tan x appearing here. It is the differential of sec kx, so then if we go backwards, integrating sec kx tan x gets us actually sec kx, so we have got that there in the formula book. So let's go and apply the integration now. So before we can do that, I'm going to get all of them to a particular form. Now when we're integrating separate terms like this here, it's exactly the same as saying sec integral of each of the terms individually. Okay, so you can integrate them individually, which is the same thing. I'm going to get them all to the same form first, a form that I can integrate. So sec squared x is fine. The 2 sec x tan x form is absolutely fine because that's in our standard results in the formula book. And the tan squared x I'm going to write down as sec squared x minus 1. Okay, so I've tidied that up a bit. Now you can see here then this gets us 2 terms involving sec squared x, so I'm going to tidy that up a bit. I get 2 lots of sec squared x plus 2 sec x tan x minus 1 dx. Now I'm ready to actually integrate them, because all of these are things that we can integrate using standard results given to us in the formula book or ones that we already know. So starting off with, I'm going to integrate sec squared x. So sec squared x, we can see here, gets us, well, sec squared kx gets us 1 over k tan kx. So this will then give us, well, the 2 just stays as it is. That's just a coefficient. It's what's multiplied by. So the integral of sec squared x becomes tan x plus, let's look at this here, sec x tan x. Okay. So I'll go and focus on that here. So there's sec x tan x. I'm just going to focus on that. Don't worry about the 2. The 2 is just a number in front of it. Okay, so you can just imagine this being just a number in front, so you can keep that out separate like that, just like we did with the sec squared x term. So what is the integral of sec x tan x? Well, if you look at this here, we can see that sec x tan x gets us sec x. Okay, so if we were to differentiate sec x, we would get to sec x tan x. So the integral of that is sec of x, and the 2 is just essentially what it's multiplying. It's 2 lots of that. And then integrating minus 1 gets us minus x plus our constant of integration, c. Okay.